Okay, so welcome to another TFA Tech Forum. So we've got Sumit with us today to talk about encrypted FIP support. So we'll do that presentation and do Q&A. The people. There you go. And then there was a request last time if we could have a follow-up on measured boot discussion, so we'll see if that's still required after the presentation and do that. Otherwise, as always, if we have time at the end of the meeting, we can talk about anything that people have on their minds, especially things from the last 2 weeks of discussions on the mailing list. So I'm gonna stop sharing my screen and ask Sumit, could you please share yours?
Yes, sure. Are my slides visible?
Yeah, they're visible. They're not in presentation mode or anything like that yet. Oh, there we go. Indeed they are. So, yeah, they are now. So without further ado, I'll hand over to you, Sumit, to present your topic this week.
Yeah, thanks, Jana. So hello everyone. Welcome to this TFA Tech Forum session. So in this session, we will discuss about the FIP encryption feature that is present in the TFA mainline. So as the name suggests, here we are looking at confidentiality protection for the firmware which are packaged as part of FIP. So here FIP refers to the firmware image package. And that is the commonly used format when it comes to trusted firmware for A-class devices. So a quick introduction about myself. This is Sumit Garg, working as part of support and solutions team Linaro, especially responsible for activities related to security and toolchain. So let's get started, but please feel free to interrupt me in case you have queries in between. So this is the overall list of topics I have to cover up today. So starting with the FIP encryption overview, the assets which we are trying to protect, and the use cases which are driving for this FIP encryption feature. Secondly, we will discuss the implementation challenges when we try to implement this FIP encryption feature, such as the secret key protection, and how do we manage the keys, whether it being a device unique key or a class-wide common key, and what happens when encryption and firmware signature comes together. And lastly, how does the encryption could impact the firmware update. And the final section will discuss the implementation details as it's currently present in TFA upstream. So starting with the FIP encryption overview. So as mentioned, FIP refers to the firmware image package. And here the encryption allows us to achieve confidentiality protection and in turn integrity for firmware image that is bundled as part of the FIP. So here we generally prefer to use the symmetric encryption technique as the asymmetric encryption is generally slower and there is boot time limitation that we have when it comes to the trusted firmware. Secondly, we would like to have the integrity of the encrypted firmware blob. That's why we try to use authenticated encryption constructs such as AES GCM. Now coming on to the assets, the possible assets which we are trying to protect. So firstly, the software IP. So it allows us to protect the software IP from any kind of unauthorized access or the misuse of the software IP. And secondly, the encryption allows the firmware image to act as a secret store as well, though it's very unlikely to be suitable for very high value secrets. And lastly, the implementation details. So the encryption makes it harder for any attacker to develop any kind of exploits for the vulnerabilities that may be present in the hardware, present in the firmware. So thereby, it's basically making the reverse engineering thing difficult for an attacker. Now, the use cases which we are driving for this FIP encryption feature. So the major use cases are the software DRM robustness rules, which are driving the requirement for this feature, which would like to make it harder for the trusted execution environment to be reverse engineered. And therefore, they would like to see that trusted OS is not just signed, but encrypted as well. So the assets they are trying to protect are the DRM software IP, as well as corresponding implementation details. Now let's come on to the basic implementation for an encryption feature of the firmware. So here this image depicts that there is a shared secret key that is among the OEM or service provider and the device itself. So the OEM uses that secret key to encrypt the FIP image using the authenticated encryption construct, and thereby flashes that onto the device flash memory. And the device itself, the bootloader uses that same shared secret key to do authenticated decryption during the boot and load it onto the memory and thereby continue the device booting system. So this is the basic implementation how an encryption technique for a firmware would look like. Now coming on to the challenges attached to it, starting with the secret key protection. So the protection may vary from one platform to another, depending on the use case and the hardware capabilities that a platform may possess. So that may be the key is derived from the secret keys, such as one-time programmable key or such, or the secret key is provisioned into the secure fuses on the device, or the secret key is provisioned into the hardware crypto accelerator itself. And lastly, the key is provisioned into the platform secure storage, such as the non-volatile SRAM, etc. So in order to address this varying requirement, we need to have an abstraction layer, which will allow us to retrieve the secret key or corresponding handle, and platform could provide the underlying implementation. So in this case, the TSA provides this API, which I have listed here, in order to retrieve that info. Now, the second challenge being the key type to use. So there could be two types of keys, one being the device unique key, or the second one being the class-wide common key. So we'll try to understand them better by discussing their pros and cons. So starting with the device unique key, which is also known as the binding secret symmetric key. So the major positive is that it limits the attack surface to a particular device and thereby provides protection against software cloning as well. And the negative being the scalability issue, as it becomes increasingly difficult to manage per device unique firmware images. Now, the common class-wide common key, which is also known as the shared secret key. The positive for this key type is it provides a single firmware image, which is easy to deploy and update. The negative being it has comparatively larger attack surface, which may often lead to class-wide attacks as well. So the final thought that came here is how can we leverage the benefits of both the key types, which we'll try to explore in the upcoming slides. So this figure depicts the process during the first boot, where we try to leverage the both key types, and it's known as the firmware binding. So in this case, the OEM or service provider has only access to the shared secret key, and it does the normal authenticated encryption for the FIP image and provision it onto the device flash memory. Now, during the device boot on the first boot sequence, the bootloader has access to both the key types, SSK and the BSSK. It uses the SSK to decrypt the FIP image and then re-encrypt that same image using the BSSK and flash it onto the device flash memory. And after that, it issues a reset. So now let's see what happens on the subsequent boot. So the bootloader will use now the BSSK key to do the authenticated decryption for the FIP blob on that is present on the flash memory, and thereby load it onto the memory and continue the device boot sequence. So in this way, we achieve the benefits of both the key types, having the shared secret key to provide a single firmware image that is easy to deploy and update, and also benefits of the BSSK, which adds the security. So now coming on to the next challenge. So what happens when we combine the encryption and the signature? So encryption and signature are two well-known cryptographic constructs, but when their combination is to be used, proper attention is to be paid towards the achievable security properties. So I've tried to list three possible combinations here: encrypt then sign, sign then encrypt, and lastly, sign then encrypt then MAC. So we'll try to discuss each of them in detail to know their benefits and compare them. So starting with the encrypt then sign approach. So as the figure depicts here, we first encrypt the firmware image and then put a signature on top of the encrypted firmware blob. So in this way, we could achieve the security properties such as confidentiality, integrity, authentication, and authorization as well. But there are few shortcomings attached to this approach as well. So in this case, only the encrypted firmware blob is non-repudiable to the OEM or service provider, where we would like to have the plain firmware to be non-repudiable, which could play a significant role when there are multiple third parties involved. The second shortcoming being when we sign an encrypted blob, it makes it immutable, which doesn't allow us the re-encryption feature that we have discussed before, also known as the firmware binding. So now let's come on to the second one, sign then encrypt. So in this case, as the figure depicts, we put a signature for the plain firmware image and then do the encryption over it. So this way we achieve confidentiality, authentication, authorization, and non-repudiation. But there is a major backdrop to this approach. That is, when we do plain encryption, it doesn't ensure the integrity of the encrypted block. So, which may often be vulnerable to the chosen ciphertext attack. Now coming on to the last one, sign then encrypt then MAC. So as the figure depicts here, we put a signature for the plain firmware image. Then we encrypt the firmware image, and lastly we put a MAC tag for the encrypted firmware block. And this way we achieve almost all the security properties, and we address the concerns for the previous approaches as well, as the MAC tag assures the integrity of the encrypted blob, and it also allows firmware re-encryption feature to work as well. So this is the approach we have chosen for TSA implementation in the upstream. Now coming on to the last challenge, being the firmware updates. So generally there could be two possible ways to apply firmware updates. So firstly, we either update the complete FIP partition, or secondly, we update individual images in the FIP payload. So while updating complete FIP partition, encryption as such doesn't add any complexity. So the updater could easily verify the overall FIP partition signature as it does before without encryption. But when updating individual images in the FIP, encryption as such does add complexity. So the updater needs to verify each individual image, which would require access to the encryption key. And thereby, either the updater needs to be a secure world entity or needs to leverage a secure world decrypt and verify service. That's all I had to discuss about the challenges. Now coming on to the upstream TSA implementation. So currently, trusted firmware supports an IO encryption layer, which is kind of a pseudo layer that can be layered on top of any base IO layer, such as the FIP layer we have discussed before. So it allows us to load any corresponding encrypted firmware payload. And as mentioned before, we have used the sign then encrypt then MAC approach, which leverages the existing TBBR chain of trust infrastructure. And we use this encrypt firmware tool in order to encrypt firmwares during the build process. And lastly, I have listed here the build options in order to enable this feature. If people are interested to enable those on their respective platforms. And for references, I have put here file links as well, so that if people are interested in details, could refer to those. So finally, about the future work. So firstly, I would like to emphasize that let's champion onto the open source security framework, which would significantly reduce the efforts to maintain custom security solutions. And secondly, contributions to improve this FIP encryption framework are very much welcome. And either the platform support is also pretty much welcome. So that's all I had to discuss in this session. And now I'm happy to take any questions or comments if there are any.
Hello, Sumit. This is Manish.
Yes, ma'am.
Yeah. So I'm just wondering, have you ever explored this encryption feature for dual root chain of trust, or is it only for TBBR for now?
Actually, that dual root feature was added a little bit later when I developed this feature. So I haven't looked at that dual chain of trust feature as such. So probably
one of the initial challenge, initial tasks we can take up is extending this feature for dual root chain of trust as well.
Okay. Yeah, sure. I will try to look at that.
Okay.
So I had so this is Raghu. I had a question about the usefulness of binding the firmware or re-encrypting the firmware with a specific key, right? So if the asset being protected is the firmware, whether or not it is encrypted with a class key or a device specific key, it is still a break one break all attack, right? So you break one device, you still are able to decrypt the entire firmware, which is the original goal, right? So maybe I missed the advantage of binding it to a particular device.
So there is software cloning aspect as well. So if you have firmware that is encrypted to a particular device, so it becomes difficult to copy that firmware to a different device which may have different device specific keys. So that's another advantage for that, to use the device image key.
Okay, but but isn't it the same firmware image that's running on all?
Yes,
on all
true.
Devices.
That's true. I agree with you. But from attack surface point of view, if you are encrypting, basically using a common key and using that for encryption, so that's I think are still vulnerable when compared to a per device key. And this is again, the software cloning aspect is also an added benefit for this per device unique key. That you couldn't clone a software, a firmware that is running on a particular device to any other device. Because if you are using a common key, class side key, then it may be possible to do that.
Well, right. So, but it seems like a device supports two modes, right? Initially, you have to support using the class key before you
Yes,
re-encrypt to the device key, right? So,
yeah.
is there? So, is it up to the platform to decide that okay, I will allow, you know, a firmware encrypted with a class key once, after which it must be, uh, it must use the device specific key. Because if you can
So,
just replace the firmware with a class key signed firmware, yeah, you're done, right?
I think I'm able to get you. So here, what we are saying is during the update process, we do this once only, and it's when you are binding the firmware to a particular device specific key, then that would boot only using that DSSK key only. So there isn't a choice then fall back to SSK. So
Okay.
that,
So you're saying the update path uses the class key and the boot
yeah,
path uses the device
yes,
specific key always.
yeah, yeah.
Okay.
Sumit, got a question about how do you identify the encrypted partition inside the FIP blob?
Encrypted partition.
Do,
I,
do you know how do you know that the image you want to load, does it mean that all the FIP is encrypted, or are you able to choose between a BL31, BL32, and BL33 which one is encrypted? I don't know if you present it in your slides.
yes, so I think you are talking about this firmware updates section, right?
Yeah, firmware update, or also the load part that you need to decrypt the image.
So in this case, we do individual images are encrypted, not the complete zip partition. So it's always the BL31, BL32, or BL33. So as you could see the build options as well. So we have separate flags for BL31 or BL32. So you could encrypt individual images and not the complete zip partition.
Okay, my question was more about at runtime when you load it, how do you identify that you must decrypt it, that it's static, or is it something that you know from a header part or something else that you
So,
know that you need to decrypt it?
so that's built into the BL2 firmware. So whether a particular image is encrypted or not.
Okay, okay, perfect.
Yeah.
Are there any more questions for Sumit? I'm not hearing any. So thank you, Sumit, for your presentation. Very interesting. I'll just share my.
Thanks, Sharma.
Thank you. Yes. Let's find my appropriate screen. Is that one? Did I share that? Are you guys seeing the TFA agenda?
Yes.
You are good. It's all right. I was expecting a big green line around it, but it's not showing. So Yeah, so we've gone through the encrypted FIP support. Thank you again for that. The slides and the recording will be available in the coming few days. I'll try to get these ones up a little bit quicker than the last sessions, which are upstream now and are available on the web page. Last time, I think Raghu, I think you asked for a follow-up discussion or a possible space for follow-up discussion on measured boot. Alexei, unfortunately, couldn't make the meeting, but I think Javier is on the call if necessary. What did you want to discuss? What did you want to pick up on?
Yeah, I think it's a couple of things. So one is my understanding is that it's being tested on top of Opti. So it would be nice if it is an FFA based application, if all the infrastructure is FFA based as opposed to Opti native, so that it's a trusted OS agnostic. The other thing I understood was that it's compiled for AArch32. It would be good if there is 64-bit support for the testing infrastructure. I think it'll be really useful.
Sure.
So those are the two comments.
Yeah, I guess on the first one, I guess when we started this work, the FFA implementation that we had wasn't as mature as we wanted. So your suggestion is definitely a possible future enhancement. I don't know, Javier, if you've got any comments on that, given that you did.
Hi. Yeah, so yeah, that's pretty much what you mentioned. So when we started working on this, we were trying to look for something that was already there, because our aim wasn't to implement a TPM, was just test what we had with something that was out there to prove that it was able to interoperate. So yeah, we just found this. We went through a couple of ideas, and then we found this FTPM implementation. I think some people from Linaro were working on that, and actually they passed me the work, and I based on the work. And so we use that pretty much just for convenience. So the repo that we are using for the FTPM, it comes from Microsoft, and what they did was just write a library, and then someone else just wrote an ARC32 application running on Opti. So it would just be a matter of write a new application using that library with support for 64-bit architectures. So yeah, I think that's something that we could raise internally to see if it's something that we want to work on, and then just schedule this for the future, I guess. Right, Jonah?
Yeah. So I guess for both really is that we'll have to internally within
a replanning exercise, orienting the deliverables around.
Sorry, I didn't.
Yes.
Not sure what that was. I think, as I was saying, I think these are possible future enhancements that we could take internally and see if we can prioritize. But as the code and everything upstream now, that it's more than you're willing for partners and people who have got a special interest in this space if they got modifications or enhancements they want to do. So they're probably the two options that we can take forward. And I will raise this with Matteo, who drives a lot of our internal arm work of the priority of things that we should work on. But as I said, more than willing to take contributions in this space as the technology is now upstreamed, and as always, looking for partner contributions.
Yeah, that makes sense.
Just to add in, so the FTPM does compile in for the ARC64. You might want to get in touch with Ilya. So we have it working in the ledge reference platform now. So in case you want to have the FTPM working for the ARC64 architecture, so he can help out.
Okay, thank you.
Yeah, so one other comment is, this is more regarding the design of measured boot, design and I guess even architecture. So I know Stuart Yoder is involved in that, but one of the things that the way it works today is that all these measurements for BL2, BL3.1 are all passed through the TTB all the way to the TPM app, right? So more recently, some of the security requirements that we've seen is, people don't want to trust mutable code, right? So anything outside of the ROM to make the first commitment of the measurement, whether it be to a TPM or to some other, secure subsystem on the SOC, right? So the way it is implemented today, I think only BL1 has a hook for the platform to deposit measurements into into a platform specific location, right? But BL2 and the way event log and all those things are written, I don't see. I think it requested this. I don't see platform hooks for it, so it would be good. That's something as well that we should consider in the near future. I'd like to hear thoughts on that as well.
So yes,
Okay,
carry on, Javier. You're closer.
I know.
To this.
I was just going to mention. I don't know if I get you at the beginning of your exposition. You mentioned that the measurements are being passed through using the DTB, right? You mentioned that.
Correct.
Yeah, actually, the measurements are not passed through the DTB. The measurements are kept in secure memory. There's also a copy in non-secure memory to be used for by the non-secure world, but the measurements are kept in non-secure memory, and what we pass through the DTB is a pointer to where the measurements start.
Right.
We don't
and my point is, it isn't sufficient that it is in secure memory, right? It needs to be, if you're using a discrete TPM, BL1, for example, must deposit the first measurement in BL1 to the TPM.
Yeah.
Right? And not just a secure memory.
Yeah, we were aware of that. The purpose of measure boot, I guess, and I guess that Alexei will be able to answer that better than me, but unfortunately he's not here. The purpose of measure boot is for those cases in which you cannot access a TPM until late in the booting process. So, for instance, we don't have a discrete TPM, and therefore we cannot extend any measurement until the whole system has boot up, for instance, as what we do on our tests. So I guess, and this will be platform dependent, of course, but I guess for a case in which we have a discrete TPM, we should be able to extend the logs earlier, maybe on BL2 or even BL1. But I think Alexei might be able to answer that better than me. So yeah, I guess we could follow up on this on the mailing list.
Yeah, I can. Yeah, I was supposed to send this on the mailing list. I forgot about it, so I'll be sure to send these comments on the list as well.
Yeah, no worries.
We can also get involved, Stuart Yoder, if you've come across him. He's one of our ATG architects who's currently working in this space and giving us advice and direction on the architectures that we need to support in TFA for measured boot. So we can get him involved as well in any discussion.
Yeah, that sounds good. Thank you.
Any other questions on measured boot? I'm not hearing any. Okay, so looks like we've got time this week to see if anybody's got any questions from the over the last couple of weeks for anything that's been discussed on the mailing list. This is a good opportunity, to have a real-time conversations if the participants are here. Unfortunately, not everybody is, but so has anybody got any things they want to follow up with from the mailing list? Scroll through it.
Hi there, can you hear me?
I heard somebody that was very
Oh.
crackly.
Yeah. Sorry, that's me. Can you hear me all right?
Just about, I think.
It's probably my mic. I basically wanted to ask, is Clang, it's not in the mailing list. I wanted to ask, is Clang commonly used as a compiler?
Sorry, I heard something about Clang. It's not in the mailing list. What did?
I'll type my question. That's what.
Okay. Do we have support for Clang? Yes, I think we do, and it should be documented in the docs links off of the off of trustedfirmware.org.
I'm not sure, but I think the question is, do people actually use it? Right? Do people commonly use it? I think that's the question, if I understand correctly.
Right. Well, I guess we do some degree of testing with it, but it's. I guess the big question is there any partners who want to or contributors on the call who say they actively use it?
I also want to ask if for testing at Linaro side, do you use Clang or the GCC? What's the preferred toolchain?
What's the preferred tool chain was what I heard.
Yeah. So I mean, can we expect problems with Clang if we compile with Clang compared to GCC, or is it fully supported? It's an equal citizen.
So I don't think you should expect any problems, but of course, if there are issues found, we'll be more than willing to fix them.
So if you follow the read the docs, you should be able to build using Clang. It's a bit different than using GCC, because for linking you need to still use GCC toolchain. So it's kind of bit different than what it's not straightforward, but if you follow the document, you should be able to build it. If not, then let us know. And I know people, I know somebody was maybe a week or two ago, somebody was trying to build it and they were able to, yes.
Yeah, and I think in our CI we do test
yes,
at least.
Yes. In our CI also we do. Yes.
But most of the tests are using GCC, but at least we test it if it builds correctly or not.
I see. I did notice that in docs there is this mention of Clang where it says that it searches for the CC string or for Clang, and if it finds it, then it can use Clang linker as well. So I'm only playing around right now, and I found a bit of a problem at linking stage. Otherwise, it was okay. At linking stage, the BL31.ld.s, that file, the preprocessor is basically killing some problems there.
Yeah, so I can answer that. So I think if you have Clang LLVM 9 or after, I think you can use a LLD as a linker. Yeah.
Right. Okay.
LLVM
The
9,
problem is when.
Go ahead.
Sorry. I was saying the problem happens when at the preprocessing stage. So preprocessing of bl31.ld.s, right, that file, it just doesn't recognize the symbols in there, and I think I feel the problem is it basically just takes out every symbol it takes, says this is not recognized, and the command it uses Clang ++. I'm still investigating. It's just very early for me, so I was wondering if there was something known about this kind of stuff.
So yeah, I'm not aware of any issues so far building TFA. Yeah.
Sure. Okay. Thanks. It's something that probably I'm doing wrong, so I'll investigate further. Thank you.
Okay. No problem.
Yeah, if you've got any questions, I mean, feel free to use the mailing list.
Yeah. Sure. Yeah. I just wanted to kind of do my own research first before posting it. Yeah. Thanks.
Sure, of course. So, was there any other questions from the mailing list, or that people want to cover? If not, then I think I can give everybody 15 minutes back of their time. Thank you, guys, for everybody for attending today. As I said, over the next few days, I'll get round to updating the website and make the presentation and this recording available to people. Otherwise, thank you very much, and I'll speak to everybody, or we can talk to everybody again in 2 weeks' time at our next Tech Forum meeting.
Thanks. Bye.
Thank you.
Thanks.
Thanks.
Bye. Thank you.